Let's move forward with this nice paper on deep learning for Earth system science. Here we are about deep learning challenges in Earth system science. Again, remember, I'm being very brief. I'm not reading all the text. The similarities between classical deep learning applications and geoscience applications outlined above are striking. So I skipped some of it. Yet numerous differences exist. For example, while classical computer vision applications deal with the photos that have 3 channels, red, green and blue, hyperspectral satellite images extend to hundreds of spectral channels well beyond the visible range, which often induce different statistical properties to those of natural images. So just to remind ourselves, the classical deep learning and geoscience applications, there are lots of memories involved, there are teleconnections involved, so you cannot look at monsoon here and interpret everything just on this data, because there are influences coming from far away in, from the Arctic, from the Antarctic, from the Pacific, from the Atlantic, and so on and so forth. And a hurricane, for example, grows based on, let's say, the heat content in the ocean. The heat content takes time to build up, but when the hurricane passes, it can chew it up very quickly. So as it keeps moving forward, you cannot just look at what is existing now. Maybe you need to worry about the build-up as well. So these memory effects are very important in geoscience applications, but these are additional examples of hyperspectral images versus just RGB images, for example. This includes spatial dependence and interdependence of variables, violating the important assumption of identically independently distributed data. So if you have temperature, precipitation, winds and rainfall, they are not independent. They are all related to each other in a very dynamic and thermodynamic way. Additionally, integrating multi-sensor data is not trivial, since different sensors exhibit different imaging geometries, spatial and temporal resolution, physical meaning, content and statistics. Sequences of multi-sensor satellite observations also come with diverse noise sources, uncertainty levels, missing data, and often systematic gaps owing to the presence of clouds and snow, distortion in acquisition, storage, transmission, and so on. And you can imagine the scale of the temperatures themselves are very large compared to rainfall, and humidity has got this exponential dependence on temperature, and so on and so forth. In addition, spectral, spatial and temporal dimensionalities raise computational challenges. Data volume is increasing, and soon it will be necessary to deal with petabytes per day globally. At present, the biggest meteorological agencies have to process terabytes per day in near real time, often at very high precision, so 32-bit or 64-bit. Further, while typical computer vision applications have worked with image sizes of 512 by 512 by 512 pixels, a moderate resolution around 1 kilometer global field has sizes of approximately 40,000 by 20,000 pixels. That is 3 orders of magnitude more than what deep learning algorithms have been typically dealing with. So this is a nice example. Here is a machine learning task, and here is a science task. So you're looking at object classification. You easily see a cat and a dog, and machine learning can easily do this part. Or you have semi-resolution and fusion, so you have now very easily usable PC-based or tablet-based or even iPhone-based tools of taking fuzzy photos and filling them up magically, and here is the ground truth, and you can see the reconstruction of what can happen. So let me take this call because it's very important. Sorry, I got cut off there, so I'm gonna restart. I have to give a talk tomorrow, so the organizer was calling, and unfortunately I need the details. The idiots haven't sent me the details. So well, you shouldn't say idiots on record, but when they don't organize properly, it's just a waste of time. So we are looking at image of 8 by 8 input, 32 by 32 samples, and the ground truth. So let's read what the caption says, for examples of typical deep learning applications in the left panels, the geoscientific problems they can be applied to in the right panels, and we are looking at this is the earth science task, this is the video prediction, and this is the short-term forecasting. So I cut it and split it. Actually it's A, B, C, D, and then you have how to look at it. You have to order them properly. So object recognition in images links to classification of extreme weather patterns using a unified convolutional neural network on climate simulation data. So there are technical details, let's not worry about it. And B is super resolution applications relate to statistical downscaling of climate model output. Again, a lot of technical words there. And C is video prediction, is similar to short-term forecasting of Earth system variables. And the right image is courtesy of Sujan Koirala and and D here is language translation links to modeling of dynamic time series here, and left image courtesy of somebody else. So basically you get the idea that object classification and localization is very easy for RGB images, whereas if you think about fusion, super resolution and fusion, etc., you want to use the same idea now for Earth system tasks. You can see how complicated it is, the scales, but also the details, and it's not just an RGB anymore. You have many colors, and you want to take kind of a global image and let's say somehow produce, in this case, a statistical downscaling and blending for the US, and you can see that there are moving systems. So it could be a thunderstorm that is going from the west to east, and if you just focus your deep learning on local data, then you obviously are likely to miss what the history and memory brings to the analysis, or actually the event itself. What happens here depends very much on how it's been coming along and what happened here. For example, you could be getting suddenly an infusion of moisture from the Gulf of Mexico that makes this system explode here, while it may be much lighter as it comes along here. I'm just saying it as an example. And here you are looking at video prediction. So time is going in this direction. Here are two people walking along, and the data is given at this point. So predict future visual representation, it basically linearly or somehow interpolates and says these people working at this speed are going to get out of this frame somehow in the t+1 time step. And you want to do that same approach for short-term forecasting. As we said, it could be just nowcasting, which is, let's say, few minutes to a few hours, or it could be a few days as well. So you can see what is meant by that here, stacked images in time. So time is going in this sense, let's say, and also in this sense. So depends on whether the satellite is doing it, or whether model is doing it, or whether it's just a data driven empirical forecast, or if it is downscaling of a dynamic forecast that is using past data to interpret observations and model together for the future. Okay, so here is language translation. Sorry, I won't say much here. So here it's saying softmax and decoder, encoder, embed. These are very technical things, and it says he says he loved to eat, and then it is some garbled thing here, so it has been converted into coherent text. So similar thing can happen here in a dynamic time series modeling, so real versus predicted humidity values. So you can see that humidity can be obviously very variable in time, but when you use this kind of learning, you may end up with a very smooth looking curve, and it is obviously extrapolating and doing something to give you predictions, but some places the errors are large and positive, or errors large and negative. Some places it matches very well, and so on. So this cycle is done very well, for example, but here you have peak error and a trough error here. You don't want to produce new peaks and new troughs in predictions that are not there in the data. So just jumping ahead, the most promising near future applications include nowcasting, that is prediction of the very near future up to 2 hours in meteorology, and forecasting applications, anomaly detection and classification based on spatial and temporal context information. So a few examples. A longer term vision includes data driven seasonal forecasting, modeling of spatial long range correlations across multiple timescales, modeling spatial dynamics where spatial context is important, for example fires, and detecting teleconnections and connections between variables that a human may not have thought about. Okay, so let's come back and read what the main issues are. This one got interrupted and then I restarted, so I don't know exactly how long it is. Because when you resume recording, it shows like it may be 17 minutes, but when it removes the gap, the blank space, then it may be just 10 minutes or so. So hard to guess. So we'll come back and look at what are the main issues we are dealing with in terms of integration with physical modeling. But this one is about deep learning challenges. So we'll come back and look at some specific challenges we face in applying deep learning to a system science. Okay, so I'll come back and do that. So it'll have a couple of more podcasts at least, but that's okay. This is a nice topic. We'll take our time. Okay.